My name is Samuel Howard. I'm the group leader for Group 3 for Experiment 1, the Clapeyron experiment. The objective of the experiment is to determine the latent heat of vaporization of water at different pressures and temperatures using the Clapeyron equation. The Clapeyron equation gives the relation between saturation pressure and temperature, specific volume, and enthalpy. Basically, it allows us to measure something that's hard to measure physically, such as enthalpy, by things that are easy to measure physically, like pressure and temperature. So the equation is there. You have the derivative of the pressure with respect to the temperature is equal to the latent heat over the temperature and the specific volume. However, in that form, it's harder to use, so we use the ideal gas law to simplify it, knowing that PV equals, well, pressure and volume is equal to mass times the gas constant times temperature. We can rearrange it, so now we see that the derivative of the pressure with respect to temperature is actually the latent heat times the pressure divided by the temperature squared times the gas constant. Here's a plot of the given data points from a steam table and a curve fit to that, an exponential curve fit over the data set. As you can see, it's important to note that towards the ends, the curve doesn't fit quite as well as it does in the middle. We'll get into that in a second. But using Excel, an exponential regression was done on the data, which gave us that number, that equation, which would be useful in the next step, which is actually to find the derivative of that equation. And as you can see, this derivative is what we're going to use to determine the latent heat in the Clapeyron equation. So here's a sample calculation for pressure at 1 kPa and temperature at 280 Kelvin. Like I said, we took the derivative of the pressure with respect to temperature, and plugging into that equation, we were able to then plug it into the Clapeyron equation to find the latent heat of vaporization for the water at that pressure and temperature. When comparing it to the steam tables provided, like in the book, it's pretty far off. I think that is due to the fact that, as I said, at the extremes of the curve fit, the data doesn't fit as well. And so whenever we took the derivative of that regression, it kind of threw our data off at the endpoints. And you'll see at the next calculation, which is in the middle, which is more in the middle of the curve where the data fits a little more closely, when comparing it to the steam tables, it actually fits a lot closer. But again, you're going to have some error because the regression isn't exactly accurate to what the physics would be. Here's another sample calculation towards at the end of the spectrum, and again, it gets further off by a lot, again, because the regression doesn't fit as well. So now I'm on to the experiment apparatus. This is the setup we'll be using for the Clapeyron experiment. We're going to be boiling water in a beaker, number 1, on a hot plate, number 2. We're going to be measuring the temperature with the thermocouple, labeled number 3. Number 10 is the computer that's going to be recording the data from that thermocouple, and the pressure from number 4, which is the analog pressure transducer. The vapor is going to flow into the vacuum, which is controlled by number 7, which is the vacuum control valve, and the vacuum 8 and 9, and the vacuum reservoir 9, and then the air bleed valve being number 6. It'll make more sense once we actually talk about the procedure. To start the procedure, we have to turn the vacuum pump on to bring the pressure in the beaker as low as we can. Ideally, we'd be able to get it to 0, but that's physically impossible. So we get the pressure inside of the beaker as low as we can, and then we turn on the hot plate and boil the water at that low pressure. Once the water begins to boil, we got to make sure that the thermocouple is submerged. But once the water begins to boil, we'll begin logging data, and then we'll slowly close off the vacuum pump to cause the pressure to start to rise due to the boiling of the water and the specific volume increasing of the water. Now it's important that we don't turn off the vacuum pump too fast, because that will cause our pressure to rise too quickly. And as we know, as pressure increases, the temperature required to boil water increases, and we got to make sure that they're coming up at the same time. Otherwise, the water won't boil anymore, and will no longer be at the saturation pressure and temperature, and then we'll have to start over. So after we do that, as the temperature rises, the data will continue to be collected for the pressure and saturation temperature. Now, before the pressure reaches atmospheric, we're going to want to open up the air bleed valve, and this is so that we don't have positive pressure inside of our experiment, risking it becoming a bomb. After the water reaches boiling at an atmospheric pressure, then we'll stop taking data and turn everything off and let everything cool down. And that is it.